Hello. Uh, Hello.
Hello, yeah,
Am I audible?
audible, audible. Audible.
Mm. Okay. We'll wait for 3 minutes more. Then we'll start. Have you all registered for the examinations for getting the certificate?
Yes, I have registered.
Yeah, yeah. Ashim Kumar Das, you? Hello. Good. Okay, okay. No issue, no issue. No issue. Okay. The Mukesh, what do you do?
I am a chemical engineer working in Adani Group, Ahmedabad, Gujarat.
Yeah, yeah. That's very nice. Oh, now you are dealing with you are dealing with some project, I think.
Yeah,
What kind of role?
mainly we are in natural gas, and
Oh yeah,
but in future maybe explore with the hydrogen energy.
Achha, that's very nice. I mean, you were dealing with now natural gas, and the natural gas, the product is kind of what the product you were refining from natural gas.
So, see, natural gas basically it's a CNG and PNG. So
Yeah,
we are
yeah. Oh,
supplying, yeah. So we
I
are
understand.
supplying this, yeah. We are supplying this natural gas to industries,
Yeah,
various type of industries,
yeah.
and
I mean,
as well as yeah, households also and vehicles also.
yeah, that means you should know, you will be habituated that the compression unit and like these things you were dealing with or something else.
We are dealing with mainly see industry part as far as the industry is concerned. So our objective is to replace this fossil fuels, maybe coal or other, with hydrogen. So what are the options that we are exploring?
Exploring.
And
Yeah,
what,
that's it.
yeah, and what would be the cost-effective way? And in future, also the government is trying to replace the petrol or CNG with this hydrogen. So
Yeah,
how this will impact our business? How we'll cope up with the change? So
yeah.
that till this exercise we are working on this. So maybe in future, again we'll be
It will be
thinking on
helpful.
hydrogen plants also.
Yeah, yeah, that's very nice. Your plant is at
Ahmedabad, Gujarat itself, and Kutch
uh,
also. We have so many plants in
Achha.
Kutch. But basically,
That
uh,
is the
uh,
primary refinery of uh, Gujarat. That is Reliance
yes, yes, Reliance Jamnagar, just near to
Jamnagar.
that.
Reliance
Jamnagar,
Jamnagar.
yeah.
Yeah, yeah.
Yeah, so
Okay.
it's a western part of the India,
Yeah,
extremely western part of India, Kutch and Jamnagar.
Yeah.
So you are in east and
That
I
is
am in
that is the
west
I
side.
think that is the biggest petrochemical industry till now.
Yeah, that complex is the biggest one.
Acha, that complex is the biggest. That's very nice. Okay. Anyway, we'll start.
Hello,
Yes, yes.
hello.
Hello, hello. Yeah, Asim Kumar Das. Yes.
Yeah,
Yeah.
sir. Am I audible now?
Yes, yes, yes.
Yeah. Yes, I am working with Mott McDonald. So I am working as a consultant
Yeah,
in engineering field. So we deal with, I mean, in energy sector, especially in power.
yeah.
Uh, so now is the transition period of power. So we are shifting from the thermal, especially the coal in India, to coal
As it
gas
is
and now to the renewables.
renewable.
Uh, yes, like we are working now with battery storage system, then wind power, then the solar, of course.
Different kind
Then
of renewable sources.
yes, and the hybrid systems. So along with these, these hydrogen also we are expecting in near
Uh,
future.
Hydrogen means you have to explore the electrolyzer cells, kind this.
Yeah, I have little experience. While I have actually about 22 years experience in power industry. So
Yeah.
while working in thermal power plant, we there is most of the power plant we have small hydrogen generation plant.
Yes.
So there also is the electrolyzer, though it was a very small part
Very
of the whole process, but don't know inside of the or the nitty-gritty of the technology of those.
the technology is very easy, but capital cost is very high. All the instrument, all the setup is very costly. That's why it is difficult to place or difficult to commercialize here in India. And all the things are coming from abroad. All the instrument, all the material. That's why the assembling part is done in India only. That's why difficult to exploring all the things.
Yes, sir. You will find I have logged in from two devices. Actually,
Yeah.
from my
Okay.
laptop, I am unable to
Okay. Okay.
talk.
No
So
issues.
that's
No
why.
issues.
Yeah.
No issues. No issues. Okay. We'll start. Okay. Uh,
And the compression system. So I am little bit aware because we did that all that compressed air system in power plant.
yes. Yes. Okay. That part today we'll going to discuss.
Yes.
Yeah. Okay, this is week 7 lecture series. Uh, Today, basically, we will discuss the storage systems and compression system and compressor unit. Whatever the different option that we can store hydrogen, and what are the different process involving in the storing process of hydrogen. Okay. Here in the first, that is just I am taking. Okay. First is the hydrogen compression. That means hydrogens have to compress. Otherwise you can't store it because hydrogen has a very low density at atmospheric conditions. NPT, a standard temperature and pressure, the density is very low, that is 0.089 kg 89 kg per meter cube. That means meter cube. That means in 1 meter cube volume, only this much of hydrogen, only 0.089 kg of hydrogen, that means 89 gram of hydrogen. Okay, that much of hydrogen you can store. But this very small amount of hydrogen cannot be useful for the mobility of the industry or for any mobile industry or automobile industry. That's why you we have to compress the hydrogen such that in 1 meter cube volume, such that in a confined volume, such that we can more and more amount of hydrogen we can store. Okay, this is the main target. How can we compress the hydrogen? There are two options: mechanical compressors. Mechanically, hydrogen can be compressed, and the non-mechanically compressor. I mean, this is sort of chemical process. Okay, non-mechanical process or chemical process. In mechanical compressors, you have already little bit of aware of the mechanical compressor. Like you have, all of you have seen the compressor in bike or cycle store that they uses compressor. This compressed, they uses compressed air, and this compressed air is pumped in your cycle tubes or motorbike tube. Okay, that compressed air, in that case they compress the air, but our main target is compressing hydrogen. There are different between the hydrogen compressor and air compressor. What is the main target, or what are the main challenges in between the hydrogen compressor and air compressor? You know that air has a much higher density than the hydrogen. Hydrogen has a very low density. The density of the hydrogen is very less, and air has comparatively higher density. Okay, and the diffusion rate of hydrogen is very high. The diffusion rate of hydrogen is very high, and the diffusion rate of air is not so much high. It is less compared to the hydrogen. If the diffusion rate is very high for the hydrogen case, we have to take extra care for compressing the hydrogen. Why? Because it should be proper sealed. Otherwise, hydrogen can easily diffused. Rather, we will lose hydrogen. Okay. The so we have to develop one system that is totally sealed system or hermetically sealed system, such that suppose you are compressing the hydrogen, you are developing on compressor unit like positive displacement type reciprocating compressor, but the material and all the sealing component should be extra care, such that no hydrogen leakage will be there. But air is easy to compress, and air, the leaking of air is less than the hydrogen. And as you know that the hydrogen is very explosive gas. As we compress the hydrogen, its temperature will be high, the pressure will be high, and corresponding the temperature will be high. As it is very explosive gas, or the ignitions very highly ignite, ignition probability is very high. That's why you should have extra care. Like, what the extra care to save the auto ignition, like different sort of cooling arrangement systems, such that the temperature will not high during the compression time. Okay, these are the major challenges you have to think. And the different sort of heat exchanger you have to arrange, such that during the compression time the temperature will be high, and this sort of heat exchanger will remove the heat from the compressor, hydrogen compressor system. Okay, these are the major challenges you have to keep in mind during the hydrogen compression. Okay, but the air compressor is very easy. There is not so much temperature high. This if the temperature is high, the air is not so much explosive gas. Okay, so under the mechanical compressor, there are the positive displacement type compressor and the dynamic. Okay, a positive displacement type compressor, you know that the reciprocating compressor. Reciprocating compressor means that the simple piston and cylinder. Okay, we will discuss it. And the diaphragm means that the one, suppose one movable part is there. This is vibrating, like this is vibrating like this will keep positions in here when the pressure is applied, and then the this in this time the hydrogen inlet and outlet will occur. Okay, the diaphragm means this is one simple sort of. Okay, some students are waiting. 1 minute. Okay, okay. The first one is the reciprocating compressor. Next one is the diaphragm compressor. Diaphragm is some sort of this kind of arrangements. It will vibrate, and the inlet intake and discharge of the hydrogen will occur. Then coming to the, just wait, some other students is actually, I always prefer just to join the students at proper time or schedule time. Otherwise, it's a bit difficult to manage. Okay, anyway. Okay. Next is the linear compressor. Linear compressor, some sort of advantages are there for the linear compressor. Like it is reciprocating compressor is a very noisy and it is very vibrating system, and the compression's efficiency is lower than the liquid compressor. Okay, and the contaminations of oil, different sort of oil used in the reciprocating compressor, just to avoid these sort of contaminations and avoiding noise and the vibrations. Okay, linear compressor and liquid compressor have been developed. Okay, next is the dynamic compressor. Dynamic compressor, under the dynamic compressor, the centrifugal compressor. The centrifugal compressor is simple, same arrangement like centrifugal pump. Whatever the pump is used for moving the or taking off the water from ground floor to uh, above. Okay, this is called centrifugal pump. The centrifugal pump is used for carrying the water from the ground floor to first floor, second floor, third floor, or in the water tank kept in up. This sort of centrifugal compressor is also used for the hydrogen compressor. Next is the mechanical compressor. Why the mechanical development of the mechanical compression have been done? Because this mechanical compressor have some sort of disadvantages That's why the scientists have been thought that they should go for the non-mechanical compressor just to avoid the noise and the vibrations and the some sort of contaminations, oil contaminations. Okay, and just to improve the efficiency. Okay, there are the electrochemical compressor. We will discuss. Uh, okay, electrochemical compressor we will discuss. It is same thing like we have discussed the hydrogen gas separator unit. Okay, membrane hydrogen gas production and the metal hydride compressor. And the adsorption metal hydride compressor means that the metal hydride means that the suppose this is nickel Ni. Ni will react with the hydrogen and it will form metal hydride, nickel hydride. Okay, nickel hydride. Okay, that means the nickel is uh, reacting with the hydrogen and it is absorbing the hydrogen molecules. Okay, that's why hydrogen can be stored in the nickel in the metal hydride form. Okay, this is also very useful. And next one is the adsorption based compressor. Adsorption based compressor, that means different sort of chemicals like MOF. Okay, MOF is a very high surface area, and very porous kind of material. In this porous kind of material, what happens that the hydrogen will be trapped into its porosity. Okay, this is how the hydrogen can be stored, or when the larger amount of the hydrogen will be trapped into the metal organic framework or activated carbon. Activated carbon also have the high porosity. Okay, previous class we have already discussed. This sort of material having high porosity, the hydrogen can be trapped and hydrogen can be compressed. Larger hydrogen molecule will come and in a confined phase, and they will be compressed, and then they will be stored in the porous material. Okay, like MOV activated carbon. This are. And the cryo compressions means that the cryo means that the liquid compressions. Okay, uh, the scientists have thought that some sort of gas compressions is not till up to the mark. We have to use the liquid compression such that why the cryo compressions is useful. In which industry cryo compression is useful? You know, aerospace applications, whatever the rocket satellite is uh, you, all they uses the liquid hydrogen because the you rocket or rocket propulsions, during the rocket propulsions you cannot make a larger rocket. Okay, because considering all the design part. Okay, you have to make a max to max lower volume or lower size of the rocket. Okay, you have to accommodate all the fuel tank and all the accessories for research purpose. Okay, that's why that's why the aerospace applications they uses the liquid hydrogen or cryo compressions is useful in that case. Okay, this is the overview of the hydrogen compressor. We will go one by one and we will discuss. Firstly, we will discuss positive displacement type. Positive displacement type. Okay, before coming to the positive displacement type, you have to you should know some basic systems of the. I think all of you, I think most of the people know the piston cylinder arrangement. This is the cylinder. Okay, this is the cylinder. Okay, and this is the piston. Okay, this is the piston, and this is the connecting rod. Okay, this is connecting rod. Okay, and connecting rod is connected with crank and crankshaft. This is the crank, this is the crank. Crank has a rotary motion, rotary motion, rotary motion, and this connecting rod has a linear motion, linear motion. And this is the center of the circle. Suppose in that path, the circle will crank will rotate in the rotary motion. Okay. When this crank, this is called crank, CRANK, crank. When the crank is rotating in this path, then this connecting rod, this is connecting rod. 1 minute. This is connecting rod. This connecting rod is moving up and down. This this is piston. The piston will compress the hydrogen gas. Okay. The piston has a certain limit. It will not go to the piston head. This is piston head. Okay. This will not strike the piston head. There will be some clearance. It is called clearance volume. Okay. It's called a clearance volume. Okay. And this mark is called top dead center. This is some basic terminology you have to remember actually. TDC. And these pistons will suppose this connecting rod, if the come in that positions, the pistons will come here. When the piston come, this is called the bottom dead center. Beyond that, the piston cannot go. Okay, this is called the bottom dead center. Okay. Okay. When the piston come to the top dead center in that position, the intake of the hydrogen will occur. That means that the hydrogen will, when the piston will come to the bottom dead center, okay, the hydrogen will be intake into the cylinder. Whole cylinder will be filled up with the hydrogen gas. When the piston will go upward directions, it will come to the top dead center. The hydrogen gas will be compressed, and after that, the compressed hydrogen gas will be going out. Okay, this is the outlet of compressed hydrogen gas. Compressed hydrogen gas or hydrogen gas with high pressure. Compressed gas with high pressure. High pressure. Okay. This is why this is positive displacement type thing. Anyone of you know why this is called positive displacement pump? Piston cylinder arrangement or reciprocating pump is called the positive displacement pump. Why this is called positive displacement pump? Why? Because the answer is here. What is the definitions of the positive displacement pump? The positive displacement pump is a type of pump that moves fluid by trapping a fixed amount of fluid or displacing it from the inlet to the outlet. Okay, that means for each cycle some sort of volume of hydrogen will be compressed. Okay, for each cycle, for adding a large number of the cycle, large amount of the hydrogen will be compressed. Okay, for each cycle, one by one cycle, the hydrogen gas will be compressed or air will be compressed. Okay, this sort of technology or process is called positive displacement pump. Unlike hydrogen centrifugal pump, what the centrifugal pump does, like centrifugal pump, suppose this is centrifugal pump, whatever the pump is used for taking the water at the high rise building, this is the pump, impeller, this is the pump impeller. Okay, the continuous flow of the water is coming inside the casing of the pump and the water is going out. In place of water you can think the hydrogen. Okay, the continuous flow of hydrogen or continuous flow of the liquid is flowing. So this continuous flow of hydrogen or liquid when the flowing and it is compressed, this is not positive displacement pump. This is the continuous case. So continuous, continuous. This is not continuous. This is cyclic. See, I this is cyclic. Okay, that's why this is called the positive displacement pump. Next, I have already discussed the reciprocating compressor, the working principle in the previous slide. Okay, here the intake or inlet valve is at the top of the piston head, and the side inside at the side positions the discharge valve, delivery valve means the discharge valve. Okay, discharge valve is discharge pipe is connected here, and this is the cylinder, and this is the piston, this is the connecting rod and the crank, all the things. Okay, uh, what are the major challenges here? The major challenges is, suppose this piston cylinder arrangement is made of steel. Okay, it's steel. Okay, when the hydrogen is compressed in this steel type of compressor, there is a large tendency of the hydrogen embrittlement. Hydrogen embrittlement means that the this steel is generally ductile material. Okay, already I discussed to you. Steel is a ductile material. Ductile material has a tendency of the failure tendency better than the I means uh, failure tendency is something different from the brittle material. Okay, brittle material means that the whatever the example of brittle material is the glass. Glass can be break at a sudden impact. Sudden impact. Okay, you will giving some force to the glass, and at a sudden point the glass will be break. Okay, you cannot pre-assume the glass failure, but steel failure, as the steel is the brittle material, ductile material, steel is the ductile material. Okay, steel is the ductile material. Ductile material, the failure tendency of the ductile material is that cup and cone failure. Cup and cone failure means that the when the this is the when you are pulling this ductile material or steel, this failure will occur by forming the some sort of neck formations, reducing the area, then the failure will occur. So we can assume the pre-failure of the ductile material. So designing the piston cylinder is good with the ductile material rather than the brittle material, because brittle material have sudden failure. Okay, this steel ductile material can embrittle with in contact with the hydrogen atmosphere. Okay, the hydrogen will be trapped inside the steel structure. Okay, steel molecules, and this will convert the brittle material from the ductile material. So embrittlement, this is called the hydrogen embrittlement. Okay, so during the design time you have to keep in mind that the uh, what sort of material can we use that the embrittlement cannot occur or embrittlement cannot take place. Okay, and the some sort of modifications of the cylinder wall, because the you have to cylinder wall should be very smooth, and the no corrosions and no erosions and no sort of wear will there. Yeah, okay, wear means wear and tear, no wear and tear will there. Okay, next is the we have discussed that the multi-stage cylinder. Okay, multi-stage cylinder compressor, how the multi-stage cylinder compressor is assembled. This schematic diagram shows you the multi-stage cylinder diagram. Okay, this is one cylinder. Okay, there are two cylinder This is one cylinder. Okay, this is one cylinder, and here the smaller diameter of the cylinder is here. Okay, why the okay, I will come why the larger diameter cylinder is kept in the first and the smaller diameter one has kept in the latter part. Okay, before coming to that part, just I will discuss the connecting rod. This connecting rod has a linear motions. Okay, this two connecting rod are like this. Okay, in this way, first. Okay, my pen is some disturbing. When the in the first stage, low pressure hydrogen gas inlet will be there, and the hydrogen gas will inlet intake into the first stage cylinder. Okay, so the piston arrangement or piston positions will be the right hand positions. Suppose this position, and it will make some bigger area, and during the suction stage, the second stage will be compression, and during the compression of the first stage of cylinder, the second stage will be suction. Okay, and the compressed hydrogen of the first stage cylinder will come to the second stage cylinder. Okay, and the second stage cylinder will produce higher pressure of the hydrogen gas, and the more and high pressure hydrogen will be out, and high pressure hydrogen will be stored for the future applications. This is the way of the multi-stage operations. In this way, large number of the cylinder can be accommodated for getting the higher hydrogen pressure or higher compressed hydrogen. Okay, okay, what are the challenges? Challenges already we have discussed. The nature of compression, wear and friction during the piston cylinder movement, or cylinder piston is moving up and to and fro motions, up and downward directions. The wear and frictions will be there, and it will produce, or it will corrode, or it will erode the material. Okay, and the cylinder and the pistons will be damaged. Okay, that's why the use of lubrications or lubricating oil will be used just to improve the reliability and the wear. Okay, minimize the wear and the minimizing the leakage, and the life will be more. Okay, this is a very simple thing. And the use of the this use of the oil has some disadvantages also, like contaminations of the oil. Okay, if the oil is contaminated with the hydrogen, with the compressed hydrogen, you will get the contaminate hydrogen, compressed hydrogen. Okay, for that you have to arrange one another unit such that this oil can be avoided from the compressed hydrogen. These sort of challenges you have to take care during the hydrogen compression. Okay, uh, here are the some theories part. Okay, wide range of capacity and flow rate, and the delivery pressure is very high. Okay, and this reciprocating compressor has up to 1000 Newton meter cube per hour or flow rate, like this. The hydropack company has they have developed the flow rate compressor with a flow rate of 4820 Newton meter per hour. Okay, these are the sort of the company hydropack. Okay, Hitachi infrastructure. Okay, they are the reciprocating compressor manufacturer. Okay, these are the very simple things you can go through. These are the several challenges, like several moving parts associated with the reciprocating compressor. So as the number of the moving part and are the in the associated with the reciprocating compressor, so maintenance cost is very high. A large number of the moving part, so means that the complexity of the system is very very high, so the maintenance cost is very very high. And you have to arrange some cooling systems, cooling arrangement, such that during the compression time temperature will be high. That high temperature or high heat should be extracted, otherwise this hydrogen can be explosive. Okay, these are the advantages. Most widely used reciprocating compressor for the hydrogen compressor. This is the mature technology, good performance, high discharge at high pressure. This is flexible in size and capacity. Some disadvantages is like that they are the associated a large number of the moving part. Maintenance cost is very very high, and lubrications is associated. Otherwise, yeah, wear and tear will be there. So and the different arrangement of the thermal management, like heat exchanger, arranging of the heat exchanger is very very difficult, and embrittlement of the piston cylinder material is there. So just to avoiding the embrittlement, you have to take care the material design. And the last but not the least, hydrogen vibration and noise is present during the reciprocating compressor. Just to avoiding or eliminating these vibrations and noise of the reciprocating compressor, just some sort of minimizations of the noise or vibration, the diaphragm compressor or contaminations of the oil, just to eliminate the contaminations of the oil, the diaphragm compressor have been developed. Uh, this is simple things. You can go through this slide. I will not go through this slide. I will coming to the working principle of the diaphragm compressor. Okay. What are the advantages of the diaphragm compressor? The diaphragm compressor is the oil-free hydrogen compressor. Oil-free hydrogen compressed gas. You can get the oil-free or lubricating free. Oil-free. There is no oil contaminations in the hydrogen. What is the working principle? Here is also piston cylinder is there. Piston cylinder is here. Piston is moving in this directions and in this directions. Okay. The diaphragm, this is the diaphragm. Diaphragm is what the diaphragm moment is. Diaphragm moment is the to and fro motions in these directions, diaphragm motions. When the diaphragm is coming in these directions, the hydrogen gas will be compressed. The hydrogen gas inlet will be in this volume. Okay. When the diaphragm movement is in these directions, the hydrogen gas will be compressed. Okay. The same in the same way, inlet and outlet is there. Okay. Gas valve is there, and you can get the compressed. So the oil for smooth movement of the piston cylinder is in the right hand side, and here are some separator by using the diaphragm and the perforated plate. Okay, such that no oil will come in this chamber. No oil will come in this chamber. Okay, but all the oil is present in this chamber. So in this way, to and fro motions, the diaphragm can also compress the hydrogen. Okay, this is the basic working principle. Diaphragm plates material, all the operates close to isothermal process. This operates close to isothermal process. This is the main objective. The isothermal conditions, the hydrogen compression in the isothermal compressions. Why? Why the hydrogen should be compressed in the isothermal conditions? Every time we are telling you that there should be heat extractions unit or heat exchanger unit, such that during the compression of the hydrogen, the high temperature or high heat produced, and this high heat produced should be released from the systems. Otherwise, it can be explosive. And also, the isothermal compression has a low work done, low work done than the isentropic compression. So if we, so the work done is minimum, work done will be low for the isothermal compressions, means that the will give low work for same amount of the hydrogen compression than the isentropic compression. In the isentropic compression, higher amount of the work you have to employ or you have to give. Okay, so the main, always our main target is the isothermal condition compression. Okay, and this is the hydraulic and the gas circuit separated, so no contaminations with the hydrogen gas, better cooling than the reciprocating type compressor, cooling cooling in cover and high surface area of the diaphragm and the chamber cooled oil. Okay, these are the simple things. And high compression ratio too, reduce the number of the stages. As the high compression ratio, so it can reduce the number of the stages. It should not, you have not go to the multi-stage compressor, you can get compressed hydrogen less number of the stages, employing less number of the stages in the diaphragm compressor. This is the electrostatic diaphragm compressor. There the DC voltage is used just to and fro, to give the to and fro motions to the diaphragm. That's why the electrostatic diaphragm compressor. This is called the electrostatic diaphragm compressor. Okay, this is good for the small capacity or small scale industry or small amount of the hydrogen compressor. There are some advantages. This is the high efficiency. This is very compact, high throughput, lower power consumptions, less cooling requirement, and fit for handling pure gases, as there is no contaminations with the oil. Okay. Some disadvantages also, the failure of the diaphragm. You have to make the diaphragm material should be taken into considerations. Okay, complexity is little bit of higher. Okay, and the flow rate limitations, flow rate is not so much high, but the flow rate is the high for the reciprocating compressor. Okay, some sort of status here you can go through. These are the companies, they are producing this sort of they're up to this sort of compress 4 to 28 milliamp, and flow rate is 5 to 581 newton meter cube, normal meter cube per hour. Okay, next is the linear compressor. Linear compressor have been developed some sort of cryogenic applications. Here the magnetic bar is, here the movable magnet is used. This magnetic bar is moving upward directions and going downward directions. During the upward directions, these rod, or this you can say that there is a connecting rod, will push the piston to the upward directions. This is the cylinder, and this is the hydrogen gas, and hydrogen gas will be also compressed here. And this is this is basically developed for the smooth applications. Okay, very smooth applications. And as this is the magnet is used, I am not giving, suppose top dead center is not fixed here. Okay, but piston cylinder arrangement, the top dead center is the fixed, TDC is the fixed, and bottom dead center is fixed. Bottom dead center is fixed. But in that case, the linear compressor, the top dead center and bottom, the piston can move up to these positions or up to these positions depending on the property of the inside hydrogen. Okay, so this is some sort of difficulties here in the linear compressor. Okay, we have to employ some large number of the sensor, such that it can sense temperature, pressure of the gas. Okay, and according to this magnet moment will be fixed, or magnet positions will be fixed. The control of the piston, whatever I am discussing, the control of the piston displacement operating at a resonant conditions. These are the main disadvantages. Okay, the advantages, you can know that this is very compact, high reliability, high efficiency, low noise and vibrations, because there are the spring arrangement systems, and long operation life. Next, the liquid compressor. Liquid compressor is also compressed with the using of the positive displacement device. Okay, these are the very basic things you can go through. This time coming to the working principle of the liquid compression. Generally, you know that the liquid compression, the word is little uh,
Confusing.
confusing. Little confusing. Why the word the little confusing? Because suppose liquid means that you will take the water. Is it possible to compress water? Can you compress the water? Suppose
No.
sometimes during the solving of the fluid mechanics problem, let's assuming the water as a incompressible fluid. Okay, we have solved different numerical, assuming that the water as a incompressible fluid. Okay, but water also can be compressed at a very lower level. Okay, all the liquid also can be compressible at a lower level. Okay, so liquid hydrogen also can be compressed. Okay, here what happened, the two piston cylinder arrangement is there. Okay, the inlet, first one is the one pump, the liquid pump is used. Okay, the liquid pump is used. This liquid is another liquid. Okay, this pumping liquid is the another liquid. Okay, this is the another liquid. Okay, this cylinder, this pistons will go up. Initially it will go downward direction, and the inlet of the hydrogen will come, and the compressed hydrogen will go to the next cylinder, and this compressed hydrogen will be done further compression, or we will get the higher compression or higher compressed hydrogen. Okay, here here the liquid is here the liquid is used here the liquid is used by using the pump. That's why it is called the liquid piston compressor. Okay, and sometimes liquid hydrogen also be compressed in another technology. Okay, but here don't confuse with the liquid hydrogen. Liquid piston compressor means that here the liquid, as the liquid is used to compress the hydrogen gas. Okay, this is called the liquid piston compressor. Okay, so just don't be confused with the liquid piston compressor means that the liquid hydrogen will be compressed. Here the hydrogen gas is gaseous conditions is compressed, but the liquid is used to compress the hydrogen gas. Okay, this is the liquid rotary compressor, used to compress the gas with high liquid content. Rotary means this is the during the piston cylinder compressor or reciprocating compressor, a fixed amount of the gas or fixed amount of the gas is compressed, but the rotary compressor, the larger amount of the gas will be compressed. Okay, or at a continuous stage. Then the ionic liquid compress. In place of liquid, here we will use the ionic liquid. What are the advantages of the ionic liquid? Because the ionic liquid has a low melting point. The low melting point of ionic liquid. So low melting point means that the low vapor pressure. If the low vapor pressures of such liquid will use for compressing the hydrogen gas, the loss of the liquid will be very less. Loss of the liquid will be very less means that the during the continuous operations of this liquid, during the continuous operations or the long term operations, as the vapor pressure is the low for the ionic liquid, it will not evaporate easily. If the vapor pressure is low, for the vapor pressure is less, the not easy evaporate. It will not easily evaporate. Not easy evaporate. Easy evaporate. Not easy evaporate means that the loss of the liquid will be less. Okay. You have not replaced the liquid frequently. Okay. Like in the previous case, liquid compressor, if we use the water, the water has a vapor pressure is the very high. So the loss of the water will be there, and you have to replace the water frequently. Or if we use the oil in place of the water, normal oil, the vapor pressure is the high, and you have to replace the oil frequently. So just to avoid these things, avoid the maintenance, high maintenance, we will use the ionic liquid or ionic liquid compressor. And this ionic liquid compressor has a high conducting, this is the very high conducting, thermal conducting, high thermal conducting material, high thermal conductive liquid, high conductivity. Conductivity, high conductivity means that the whatever the heat is generating inside the piston cylinder during the compression of the hydrogen, it can absorb the heat. Okay. So the heat exchanger or heating externally heat exchanger you may not employ for the ionic liquid compressor. The no contaminations, these are the advantages you can go through. The main disadvantages of this ionic liquid is the corrosion is very high, because as the ionic liquid means that the liquid at ionic conditions or ionic liquid is used, it can chemically corrode the systems. So corrosion is very high. So you have to take care the material design for the ionic liquid compression. Okay. And cavitations phenomena. Okay. These are the main things. Summary you can go through. Next is the cryogenic compression. Means that the cryogenic means that the low temperature. Cryogenic means that the low temperature. Low temperature. Sometimes at the low temperature, the state will be liquid. Okay. The liquid hydrogen at cryogenic conditions means at the very low temperature at 77 Kelvin, the hydrogen will be at liquid state. This liquid hydrogen will be delivered through the cryogenic pump to the evaporator. This evaporator is also reduce its temperature, and it will, as the temperature is going down, the pressure will be high. Okay. The high pressure of the hydrogen will come. This is the twice of the volumetric efficiency of the mechanical compressor. Okay. The volumetric efficiency is very high. The technological challenges is to continuous monitoring of the thermal instance. This work, the working principle of this cryogenic compressor is the thermal arrangement, or it is working principle is the thermally heat is absorbed, sometime heat is absorbed, or sometime heat is released. Okay. In this process, the cryogenic compression is work. Require the low temperature. Just to maintaining or just to creating this low temperature, you have to pay higher amount of the money. Okay. The maintenance is very high. monitoring the thermal insulation, thermal as it is working principle is the on the thermal basis. So the thermal insulation should be there, or proper thermal insulation should be there. Next is the metal hydride compressor. Okay, it is just I am getting very late. I'll go in very speed. Metal hydride compressor, the metal, suppose nickel, any sort of metal will react with the hydrogen, it will form the metal hydrogen, and it will, that means the hydrogen is storing inside the metal interstitial. Okay, and during the forward reactions the heat is producing, that means that this is the exothermic process. During the releasing of the hydrogen from the metal, means that the hydrogen will be removed from the metal just to, or backward reactions, it is the endothermic reactions. That means you have to give some heat just to remove the hydrogen from the metal. This is the fundamental principle or fundamental reactions. And this is some conditions is written here. uh, this is the criteria requirement for the metal hydrogen compression or metal hydrogen systems. Okay, that should be high reversible capacity, fast kinetic. Fast kinetic means the reaction kinetics. High productivity, low plateau slope. This low plateau slope will be good for the higher amount of the compression. Okay, or low hysteresis means that the loss of the hydrogen will be less, and the cyclic stability should be high. Tolerance or lower towards the impurities. Impurities, there are the low impurities inside the hydrogen. Okay, as this is the chemical reaction, as this is the chemical reaction, and this is metal hydride. The TS diagram of this. Okay, just
Uh, sir, one thing that what is the meaning of high reversibility?
uh, okay. High reversibility. Suppose reversibility means
Means
reversibility.
here the amount of gas is absorbed by the metal.
Uh,
How much amount of during the reversible process, how much we can recover
exactly,
from
exactly,
that?
exactly. Whatever. Suppose this is metal. Okay, I am adding hydrogen. The hydrogen is reacting with the metal. This is forming the metal hydride. Whatever amount of the hydrogen is absorbing inside the metal, that full amount of the hydrogen should be released during the endothermic reaction process, or when we'll add some heat, when we'll give the heat to the material, the same amount of the hydrogen will be go out. So this is the reversibility. Highly reversibility means that the same condition achieved as the previous state. Okay, if the some sort of hydrogen will be adhere, or some set of metal hydride form is there, that means the lower reversibility. Okay, so whatever the reactions is in the forward reactions, that same amount of the reactions should be done with the backward reactions. Okay, this is the reversibility or highly reversibility thing.
Okay, thank you.
The metal hydride, this is the TS diagram. Okay, I have limited time actually. The first step is the 1 to 2 process. The 1 to 2 process is the isothermal absorption process, isobaric isothermal absorption process. Then the second is the 2 to 3 process. 2 to 3 process is the heating process. Okay, and 3 to 4 is the isobaric isothermal process, and 4 to 5 4 to 5 is the 4 to 5 is the polytropic cooling process, isobaric polytropic cooling process. Okay, this is the thermodynamic point of view. If you want to study this TS diagram of the metal hydride compressor, you can go through in details. Okay, and this is also the compressor. If you have any sort of confusion during the pH plot or TS plot. Okay, I will obviously help you, but here the time is something less. Okay, and this is the point of view of the thermodynamic point of view we can go through. Okay, if I will have some time extra, I will discuss it. Okay. Actually, you have to you should know that the know that the critical liquid critical conditions. This is the saturated liquid and saturated vapor line.
Yeah,
That's
pH diagram, the TS
yeah,
diagram
yeah.
of the
Saturated liquid and saturated vapor line. If you understand this one, and if you go through the power plant engineering or thermodynamics properly, okay, there we'll use the TS diagram. Suppose Rankine cycle and TS diagram. Okay,
Mhm.
if you understand this Rankine cycle TS diagram, this will be very easy to you. Okay, but for this subject, it is also important. But if you, it is not so much important, but you can go through. You should go through.
Sir, this metal hydride storage system, these are already in use, or this is in still in laboratory stage?
This is still in the laboratory scale. This is not commercialized yet. Okay. But in the research laboratory, some the researcher is doing research on this metal hydride. Okay, this is already established technology, established process, but this is already lab scale process, established technology, established process. Already patent is there, but this is not used commercially large scale in the industry applications. Some of the I have seen that the two or three industry in the world. I mean, two industry there in USA, and one is the USA and another one is the I don't know. I have not remember. The two industry they are developing this metal hydride storage compression systems. Okay, and they are also advertising this sort of arrangements for the selling purpose. Okay, they are not largely applied, largely they are not used, but commercially you can get. Okay, but in India there is no such sort of things or industry. Okay, the metal hydride storage bed systems, like usually they is used on cylinder. Okay, and a central artery, like the hydrogen will be passed through the central artery, and the hydrogen will be absorbed. The metal hydride material is placed in the annular positions. The hydrogen will come through the central artery or central pipe, and this hydrogen will react with the metal hydride, a metal. It will form the hydride, and it will store. And as the during the metal hydride formations, large amount of the heat will produce. So you have to remove this large amount of the heat. So you have to arrange the heat exchanger. Okay, and after that, large hydrogen molecule will be accommodated inside this storage bed. So the press and the hydrogen pressure will be high, and when we will heat these systems, this will react, the backward reactions will be there. It will release the hydrogen from the metal. Okay, in this way the higher amount of the compressed hydrogen you can get. And this one bed, you can arrange multiple bed for getting the higher compressed hydrogen. Advantages you can go through. Okay, electrochemical compression, this is important. The electrochemical compressions, here this is the membrane. This is the blue one is the membrane. Suppose this is polymeric, sorry,
Sir,
this is
one thing I have
okay,
one doubt about
okay,
the metal hydride compression.
okay,
When we heat the hydride which has been formed,
Hmm.
it will be released with the means, high pressure. How it will happen means because it will release.
Huh. Huh. Actually, what happened when the suppose this is a definite volume of the metal hydride and hydrogen is coming and reacting with the metal and forming the metal hydride. More number of the hydrogen is coming, more number of the hydrogen is coming and reacting. The large number of the hydrogen is coming and reacting in a confined phase, in a confined volume. Okay, the hydrogen pressure will be high. This is the basic principle. Okay,
Okay.
okay. And after the compression, they when you will heat these systems, this hydrogen gas will be released in a high pressure because initially what happened the basic thing initially the hydrogen molecule, this is hydrogen molecule, another hydrogen molecule, they have a very repulsive force. The two hydrogen molecule you cannot you can the deficit density is very very less, you cannot keep the two hydrogen molecule very close. Okay, so randomly the hydrogen molecule is very has a very large space. The distance is very very two molecule very very large distance. But we are reacting with the metal, and this by the reacting the two metal, the we can place the two hydrogen in a chemical bond with the chemical bond with the metal. That we can
Very,
place the two
very close.
hydrogen.
Yeah,
Huh.
very closely we
Very
can.
close, very close, and the larger number of the hydrogen can be accommodated inside into the metal. Okay, this is how the hydrogen will be compressed or hydrogen can be stored. Okay, you also can
Sir,
store.
sir, when yes, at certain point, this metal, the
Huh.
metal body will be metal body and the reaction. I mean, it will be equilibrium. There will be no
Yes,
no
no
absorption of
reactions.
the hydrogen.
Okay, there will be no reaction. That means the equilibrium condition has been reached, and the no hydrogen can be react with the metal part. So equilibrium condition has been reached. So at that positions, you have to give some heat for the backward directions to release the hydrogen. Okay,
So when we heat the system, so
okay.
it will start expanding, correct? So along with so
No, no, no. Now we are giving the heat. We are giving the heat just to make the or just to happen, just to happening, just to
the
create the
reaction. Okay,
backward
okay,
reactions. Okay, but
okay, okay, okay.
okay, there is hydrogen will be heating up. These are the things you can keep aside. Okay,
Okay, thank you.
okay,
Got it, got it.
okay. This is the membrane. This is the membrane, polymeric membrane. Polymeric membrane. Suppose this is the polysulfone polymeric membrane, or you can the peak polyether ether ketone membrane, or amide base polymeric membrane, or cellulose base membrane. Okay. Here in the anode is positive. This is anode. This is the anode is positive. Okay. This is the cathode is negative. Okay. Here in the anode you will give the hydrogen, low pressure hydrogen. Low pressure hydrogen you will give anode. And in the anode there are the oxidation reductions will occur. Okay, oxidation reduction or oxidation reductions will occur. Oxidation reactions. Oxidation reactions means that the oxidation reactions means the oxygen molecule adding or releasing of electron. Okay, this is called oxidations, and reductions mean that the electron is adding. This is the reductions. Okay, this is the basic. This is the reduction. This is the oxidations. Oxidations. Okay, in the anode oxidations will be there, and the cathode reductions will be there. This is the very basic of the chemistry. The hydrogen will come, low pressure hydrogen will come in the anode side, this side. Okay, the oxidation reactions will be there, and it will form the H plus, and this H plus move through the membrane. This is called cation exchange membrane. This is called the cation exchange membrane. Cation exchange membrane, only the cation will pass, hydrogen will pass, H plus will pass, and this H plus will come to the cathode side means at the negative side. Negative side means at the reach of electron. This is connected with the DC power supply. DC power supply, electron will reach electron is the negative terminal. This H plus will react with the electron. Two electron, it will form the H plus hydrogen gas. Okay. In this way, you can get the hydrogen, pure hydrogen. You can get, suppose in that case, if we use the low pressure hydrogen gas with some contaminated gas, with some other gas, suppose carbon dioxide or something other. Okay. You can get the pure hydrogen gas in the pure compressed hydrogen gas. Okay. How the compressed will be there? Because there will be some the membrane should be highly stiff membrane, or membrane should be chemically enough strong such that you can get some compressed hydrogen. Okay. The if the membrane is very weak, the high pressure or compressed hydrogen gas can break this membrane. Okay. Or membrane can be damaged, or system can be damaged, but it should be mechanically strong. This is the working principle. Okay. Basic working principle, or advantages, disadvantages you can go through by yourself. Next time, coming to the adsorption based compression. Adsorption based compression, it is very simple. Adsorption like material MOF, metal organic framework, zeolite, and some carbonious material like activated carbon. This is very porous material. This porous material, one student is waiting. Okay. Okay. So you know that the basic principle, the in the porosity of the material, the hydrogen will be trapped, and the higher amount of the hydrogen will be trapped. It will be compressed. Okay. This sort of technology can be used for the compressed hydrogen as well as storage of the hydrogen for the future applications, for the future purpose. Okay. These are the comparisons you can go through. Okay. This is the history of the compressed vessels. Okay, compressed vessel. Just I will come to the compressed vessel. The basic things. Type of the compressed hydrogen. Type 1, type 2, type 3. This is the development of the uh, type of the hydrogen, compressed hydrogen tank. Okay, this is important. The first type compressed hydrogen tank. This is the compressed hydrogen tank. Compressed hydrogen tank. Compressed hydrogen tank. This is the liner. This is the outer cell. Outer cell is called the liner. This is made of the metal. Okay. This is the made of the metal. If the compressed hydrogen or higher pressure hydrogen is stored in the type 1 tank, it cannot be go beyond up to a certain limit. But if we design by using the some composite fiber resin inside the hoop region, okay, I mean that by just applying some sort of stability, or some sort of structure, or a composite structure, the stability of the tank will be high, and the such that we can accommodate higher pressure of the hydrogen. Okay. In that way, the type 4 tank is the polymeric liner. In that case, the previous all the three type of things, there was the metallic liner. In that case, the polymeric liner, as well as the outside the liner, the composite fiber is placed such that the more and more compressed hydrogen can be stored. Okay. This is the design considerations means that as the higher hydrogen compressed hydrogen can be stored, the material should be withstand higher pressure and higher temperature, and the cycle life should be high. Okay, the failure should be avoided. Such a material should be used. Okay, these are the things. What are the material you can use? The metallic for the AL6061 material, polymer, polyethylene, polyamide, and composite aramide. This aramide structure has a very high strength. Aramide structure, I think you can search, you can Google it. Aramide structure has a 100 times high strength than the steel. You can go through the Google. Okay, aramide structure. This is very good. And the nowadays carbon fiber is used for making the composite. Okay, for the high strength.
Uh, Sir, this
Uh,
aluminum AL6061, it's
uh,
aluminum or it's the alloy?
this is actually aluminium means the high. This is not actually alloy.
Okay.
And this is not actually alloy. Or you can go through the internet. I
Okay,
mean,
okay, okay. I'll
aluminium.
see. I'll see.
Aluminium has a very high strength, but I know that the uses of the alumina is used. Aluminium has a very high strength as well as a lower weight. That's why alumina is used. Aluminium is used for the aerospace applications. Okay.
Means specific strength is
Specific strength should be considered during the design
yeah,
time.
yes, yes.
Okay. Actually, if you have designed one tank, compressed hydrogen tank, larger compressed hydrogen tank, the weight is very high. So it is not very easy to handle. It is not flexible. Okay. So you have to design one tank, high strength tank. The weight of the tank should be lower such that it can be easily handleable. Okay. And simultaneously, the strength will also high. Next, I am coming for some MCQ questions. Okay. Before that. Okay. The first questions you can read. The first questions: which one out of the following compressor is non-mechanical compressor? Non-mechanical compressor. Non-mechanical compressor. Non-mechanical compressor means that the uh,
Metal hydride based.
metal hydride based compressor is the non-mechanical compressor. The reciprocating compressor is the mechanical compressor because a lot of moving part like piston, cylinder, crankshaft, and the res- uh, connecting rod is there. So it is mechanically compressed. Okay. Diaphragm compressor is also including some sort of piston arrangement, and the diaphragm is the moving part. Okay, this is also mechanically done. And the liquid compressor is also uses liquid, but it is also they also uses the piston cylinder. That's why all they are the mechanical compressor, but except the metal hydride. This is the chemically based. This is the chemically based, chemically based working principle. Next questions: which compressor has the lowest specific energy requirement? Which compressor has the lowest specific energy requirement?
I
I
think
think it is
this
also
is
D. D.
ionic liquid compressor.
Huh. Adding liquid to compression. First one is the diaphragm compressor. Acha. Before coming to the specific energy requirement means that the specific energy requirement means that the suppose 1 kg hydrogen for for compressing 1 kg of hydrogen you are giving some work done. Suppose 10 Newton work done you are giving. Okay, Newton or joule or joule. For the diaphragm compressor, the liquid hydrogen compressor, you will give only 2 joules of work. Okay, okay. This is the questions, or you have to understand the questions. What the questions is asking to you. Okay, and piston compressor is also uses larger amount of the work. That's why specific energy requirement is also high. This is very high. This is also diaphragm is also mechanically compressor also high. And metal hydrate based compressor has
You need to apply the heat. I mean,
a large
to
amount of
apply
the
the heat.
heat during the reversible cycle or during the backward reactions. Okay, but the ionic liquid compression, there is a automatically there is no such requirement of the external heating arrangement, because ionic liquid itself can take some amount of the heat. Okay, it can also help the isothermally cool the isothermally compress the hydrogen. Okay, that's why our B option is the right option. What is the major limitations of using the lubricating oil in the reciprocating compressor? Major limitations. Major limitations. Obviously, the major limitation is the contamination.
Contamination.
It's a very simple question.
Contamination, yes.
Huh. Question number 4. Linear compressor are based upon which thermodynamic cycle? Linear compressor are based on, you have to remember these things. Starling cycle. This Rankine cycle is used for the power plant industry. Power plant. Power plant. You know the, I think, power plant. This is a Rankine cycle is used. Vapor compression refrigeration cycle is used for the refrigeration cycle or refrigerant. Okay. Or this is called the reversed reverse Carnot cycle. Okay. Or refrigeration cycle. And auto cycle, diesel cycle is used.
Is for
Auto cycle is for the petrol
I
engine.
think hygiene.
IC engine. Petrol engine. Auto cycle is petrol engine, and diesel cycle is for the diesel engine. Okay. Starling cycle is used for the thermodynamics based liquid compression. Okay. Question number 5. Which compressor is suitable for high flow rate?
It's a reciprocating compressor.
High flow rate. High
To
flow rate.
10,000.
High flow rate means that the 10,000 or 1,000 uh, normal meter cube,
Meter cube
normal
per
meter cube
per hour.
per hour. Okay, this is very high amount, because this is a very frequent up and down motions and cyclic motions. So high volumetric can be generated per hour. Next one is the question number 6. This is also a remember type question. Lighter density alloy like alumina. This is like alloy like L. Liner material to fabricate cryo-compressed tank can improve the system gravimetric capacity. This is a remembering type questions.
By
You have to
9.2.
9.2. Yeah.
9.2.
9.2. This is this is very high. Okay. Question number 7. Which phenomena is termed as back diffusion? Back diffusion is very important. Question number permeations of H plus ion from cathode to anode, permeations of hydrogen ion from anode to cathode, and permeations of the hydrogen molecules from the cathode to anode, permeations of the hydrogen molecules from the anode to cathode.
I
First
think
one.
A.
First one. Though how the first one is the right? Just you draw the
Yeah,
diagram.
because in the PMFC
Ha.
that one.
Hmm.
So permeation means when it come back from the cathode to anode.
Hmm. Ha. This is the cathode position, the minus cathode position. The working
Yes.
principle is this one. H plus will
Go from
mitigate, go from
anode to
anode to
cathode.
cathode. But here is the hydrogen gas. Okay, sorry, H plus ion. Okay, This is the reach of the H plus ion. This, if the H plus ion is in this direction, this is the reverse direction. So the back diffusion, it is called the back diffusions. Okay, the back diffusions of the ion. Okay. Question number 8. Which problem occur in compressed hydrogen tank when hydrogen gas set trapped between the liner and the composite?
Blistering.
Blistering.
Blistering. Buckling, buckling. Suppose
Yes.
buckling is called like, suppose in your home, this is the column. This is the column. Column can be buckle. Okay. Suppose in your roof weight is there. Column can be buckle like this. Okay. Column can be buckle like this. This is buckling. Matlab means this is buckling. This is buckling failure. This will be bend in the horizontal directions. This is horizontal directions. This is called a buckling. And blistering is, that the blistering in the road, blistering, and plastic deformations, and fatigue, fatigue is like a cyclic loading. Cyclic loading is called the fatigue. Question number 9. Which process is used to fabricate polymer liner from polymer and monomers? The process is the extrusion process, milling process, roto-molding process, and forging process. Forging process,
You
that the what is the forging process? Forging process, suppose iron metal, iron is there here. Blacksmith, they uses the forging process. Okay, you heat the iron and you can shape different shape. Okay, this is the forging. Roto molding, it is rotating part with the molding process. Milling process, that the milling process, I think milling is the something. Milling process is used
Yes,
for
yes,
the,
sir.
yeah, gear manufacturing is the milling process. Extrusion process is, that the, suppose when you were uh, taking the Colgate or toothpaste. Okay, you are pressing at the back side of the toothpaste, and the some shape of the toothpaste, cylindrical shape of the toothpaste is coming out. This is the extrusion process. Am I right?
Yes, yes.
Uh, so answer is the C, is the correct for the 9, question number 9. And the 10th, question number 10th. What is the volumetric energy density that could be achieved for hydrogen compressed at 30 megapascal? You have to,
23.
how you can get 23?
That is with the formula, no? PV is equal to
Ha. You have to
RT.
solve actually.
Yeah.
You have to solve 30 megapascal. Okay. So how we can solve this 35 megapascal? Okay.
35 or 23?
35 na. This is
35
35 megapascal.
megapascal at
Ha.
35 megapascal.
Compressed at 35 T.
Okay, 35
So,
megapascal. Okay.
35 megapascal. So final pressure. So final pressure. This is important numerical. You can write, or you can go through. Final pressure. Final pressure is the 35 megapascal. What is the initial pressure? So obviously the
One
initial
bar.
pressure 1 bar. Ini initial pressure, that the atmospheric pressure, ATM pressure, that at ATM pressure is the 1 bar
Approximately.
approximately. 1 bar equals to how much megapascal?
Point 1.
0.1, 0.1 or 1 megapascal. So initial pressure P1, our P1 is the 0.1 bar, 1 megapascal, and our final pressure P2 is the 35 megapascal. We are compressing hydrogen from 1 bar to 35
30.
megapascal. First, we will use the ideal gas equations. Okay, I am compressing the hydrogen. That means, is it ideal process? No, it is not ideal
No, it is
process.
real process.
This is the real process. But during the calculation process, we will always use the ideal gas equations, considering that this is the ideal process. Considering assuming that this is the ideal process, assuming assuming this is the ideal process. So we use the ideal gas equations. What is the ideal gas equations? PV
Famous.
equals to N
Uh,
R T. Okay. So P equals to pressure, V equals to volume, N equals to number of the mole. So N equals to number of the mole. If you see one numerical, you can be habituated with the numerical solving. Number of mole, number of moles, number of moles. How you can calculate the number of moles of any given gas? Suppose I am giving you uh, 10 kg of hydrogen gas. In the first class, 10
2
kg of
gram,
hydrogen.
2 gram,
Ha ha
yeah,
ha.
2
Exactly,
gram gas
exactly.
1 mole.
Yeah. 2 gram, 1 mole. So we can get the number of the mole by the
Converting
total
it, yeah.
by the total mass
10,000 divided by 2.
total mass
10,000 divided by 2. So 5,000 mole.
ha total total mass divided by the molar mass molar molar mass total mass. So we'll write it as a small m, and the molar mass is the m. Molar mass for hydrogen is 2 gram. Okay, this is the number of the mole. Here n is the number of the mole. Okay, so our final objective is the density. Actually, what is the density? Here the density you have to calculations. Yeah, volumetric energy. So I think density, this is you have to call it density, because kg per meter cube is the density formula. What is the density? So our main what is the density? You have to calculate calculate the density.
So we can
Density.
use their mass, means total mass. So P equal to m by V is the density. So
Huh.
P equal to
Yeah. Just I am coming to that part. So I am deriving this formula from the starting point. Okay. So P V equals to, so m is the mass and m is the molar mass, capital M, and this is the R, character universal gas constant, and this is the T. So 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 you have to calculate the density. Density equals to m by V. So you can write that the pressure
P equal.
P equals to small m by V into RT divided by capital M. So this is our density. M by V, mass upon volume. This is our density. So pressure equals to, so formula pressure equals to density. Density I'll write rho multiply RT divided by molar mass. Okay. So what is the density? So density equals to rho equals to P by P into M, capital M, divided by R T. This is our formula. This is our formula. Okay. So put all the value in the formula. So put all the value in the formula. So density equals to rho equals to what is the value of the pressure? Final pressure is the 35.
35.
Okay, 35. So 35 megapascal. So 35 multiply molar mass. Molar mass means the 2 gram. 2 gram means that the you have to 2 gram. You have to convert it into kg. That's why 10 to the power minus 3 divided by what is the R value?
314
8.314.
joule per
Ha.
mole
During
Kelvin.
ha joule per
Mole
mole
per Kelvin.
Kelvin or meter cube Pascal, or you can write that the in the volume form meter cube Pascal per mole Kelvin or Kelvin mole. Okay.
No,
Multiply
it's not meter cube, sir. It is meter Pascal or Newton
meter cube,
meter.
meter
Joule.
cube, meter cube, meter cube. Okay.
Okay, okay.
Okay. This is the all the same 8.314. Okay. All the use for the case of the SI unit. Okay. Multiply temperature. Temperature is the at assuming that the atmospheric temperature, so 298 or 300 degree, so 298. So our answer is rho equals to, it will come around 28, 28.25, 28.25 kg, meter cube.
Okay.
But this is our answer actually. Is it correct? But if you see the answer, there is no 28 value. So
Because it
what?
is the idea.
Ha, whatever we have assumed that the ideal gas conditions, but you have to take into consideration that this is the real conditions. So this is the real conditions. If you consider, if you consider the real conditions, in the real conditions, what will happen in the real conditions?
Density will be less.
Just I have to go to the next. In the real conditions, in the real gas, assuming real gas, real gas, what one terminology we are using for the real gas? Do you remember?
Compression.
Compressibility
Compression.
factor.
Compressibility factor, Z. Z is the, sorry, small, capital Z. Compressibility factors. Compressibility factor equals to, the formula was mass of ideal divided by mass of
Real.
real. Always, for the real gas, the density is less. You also can remember, for the real gas, the ideal gas has a high density, real gas has a little less density at the same conditions. Okay. So assuming, so what is there is the here is the no Z value is given compressibility factor. So you can assuming the compressibility factor, assuming compressibility factor Z. Oh,
One
sorry.
point.
Generally we assume compressibility factor 1.2. So you can assume the compressibility factor Z 1.2. So 1.2 equals to, we can write that the density of the ideal gas, the density of the ideal gas divided by density of the real gas. Okay, so density of the real gas, uh, real real gas Rg will be density of the ideal divided by 1.2. So it was our 28 point something, 28.25, 28.25 divided by 1.2. It will come around 23.38, 23.38 kg per meter cube. This is your answer. So our option 23 near the 23, or you can also remember the value, but I am not going into the remember the value, but I am going for the calculation part, how the it can be calculated. At the different compressor level, the compressibility factor will consider different. Okay, you cannot compressibility, you cannot uh, take the compressibility factor at high compression system like 700 bar, 500 bar. You cannot take high compression unit. At that time you have to take the more higher compressor, more compressible factor, greater than 2, 3, 4, 5, 7, like this. Okay, in some numerical questions, if you solve the thermodynamics numerical questions, you will find that the sometimes the compressibility factor is 2, 7. That means that the this is working at the very high compression systems. Okay, okay, I think this numerical is understandable to you. Okay, next you have to remember some densities value for the for different calculations at NTP conditions. NPT condition At NTP condition, the hydrogen density of the hydrogen gas. What is the density of the hydrogen gas at NTP condition? 0.
0.89.
0.089. You have to remember this thing value. Okay, kg per unit is kg per meter cube. And at 200 bar, in numerical, this value you have to remember. But in the some numerical, if you face some numerical, okay, you have to assume some sort of at 300 bar, what is the density? At 300 bar, at 350 bar, 350 bar, density is density of the hydrogen is like 23.65, and 700 bar, the density of the hydrogen is 40.2. By assuming this density, we will solve one numerical. Okay, calculate the volume required to store 1 kg of hydrogen. Okay, so these things I think just in the gaseous form at NTP when the pressurized up to 350 bar and 700 bar. So at at 350 bar, at 350 bar, what is the hydrogen density? What is the density of the hydrogen?
23 point.
23.65. So 23.65 kg per meter cube. So density formula is equal to m by v, m by v. So what is the volume? The question is the volume at hydrogen volume of 1 kg of hydrogen volume at 350 bar. So volume you can find that the v equals to m by density. So m equals to 1 kg. It is the SI unit 1 kg and density is the 23.65.
Six five.
Okay. Suppose a volume, you can find out the volume, it will be in the meter cube terms, or if you want to uh, convert it into meter cube to liter. Okay, meter cube to liter, you have to multiply 1000. Okay, 1000 liter. 1 meter cube equals to 1 meter cube equals to multiply 1000 meter, means of the 1000 liter. Okay, you can calculate this value at 350 bar. Similarly, you can calculate the 700 bar. You can the value. Okay, and in the liquid form at a 220 Kelvin, in liquid form at 20 Kelvin, what is the density of the hydrogen? Sometimes you have to remember the liquid hydrogen density. Liquid hydrogen. Sometime not. You have to remember the liquid hydrogen density because at 1 bar the liquid hydrogen density is the 70.9, 70.9, 70.9, 70.9. Because you are a student of hydrogen generations and hydrogen compression and hydrogen storage and transportations. So atmospheric conditions, liquid hydrogen density you have to get into remember kg per meter cube. Similarly, you can calculate the volume of this volume of the
This will
hydrogen.
be at specific. This will be at specific temperature, correct? Density of liquid hydrogen.
Huh. Liquid hydrogen cannot be liquid in the atmospheric conditions actually. Uh, Liquid at a specific temperature like 77 Kelvin. 77 Kelvin, 77 Kelvin at temperature is suppose atmospheric temperature. 77 Kelvin and pressure is the 1 bar. Let's assume the pressure is the 1 bar.
Okay.
Okay, at that conditions you have to calculate the V equals to m by rho. You can calculate. Okay. Question number C, in the solid state at room temperature. In the solid state, solid state liquid, solid state hydrogen density is the SO like solid state density. You can remember 100 kg per meter cube. This is easy value
No,
for
one
remember.
more. In liquid form at 20 degree, 20 Kelvin, they are asking. No?
I am coming. I am coming. 20K means 20K. Okay, 20K. 20 degree Kelvin or 77 degree Kelvin. Which one is the higher? 77 Kelvin. So 77
Yes.
Kelvin, if we if we reduce the temperature from 77 to 20 degrees centigrade, the liquid is also liquid. Okay. So we can take the
Then in
density
that
of the
case, but in that case, the volume or the density will change or it will remain same. Means one bar or one atmosphere
density will
and
change.
temperature is different.
Obviously, density will change because density depends on the pressure as well as the temperature. Okay, each and every positions the temperature and the pressure will be changed, but density will not largely changeable. But
Yes.
if we if it will be like that, the density will be higher. This is the 70.9, this will be the 71 or the 71.5, little higher. This value will be the little higher, but you have not provided, if you have not provided the value of the liquid hydrogen, you can consider the liquid hydrogen at 70.9 at 77 Kelvin. Okay.
So if somebody says liquid, what is the density of liquid hydrogen? So you have to assume that that at
Ha ha ha
77
ha
K
ha
and
ha 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 ha
one bar, and
ha
the density is 70.9.
ha ha ha. You have to assume in that the 1 bar, these conditions 1 bar and 77 K. Okay.
So the volume will be volume at 20 degree Kelvin. We have to calculate with some
Volume
unique
will volume will also be changed. Volume will
Yes,
also will be changed
correct.
because temperature is reducing. That means the pressure will also change volume because the our formula is the PV equals to nRT.
Correct, correct.
All the formula will all the value will come according to this formula. Real according to this formula PV equals to nRT.
Ideal gas.
Ideal gas equations. If the temperature will be high, the pressure will be suppose temperature keeping all the things constant, volume constant, n constant, r constant, temperature will be high, volume constant, pressure will be high. Okay, suppose volume pressure is
Constant. Pressure
temperature
is
is high,
constant.
pressure
Then
is low, all the things will be changed according to this formula. Okay, you can adjust. Okay. Hmm. Okay. uh,
compare all the three cases of storage.
huh. Compare all the three cases of storage. Okay, if you calculate all the value of storage, you will get some value that at 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 NTP, the total volume of the hydrogen volume of the hydrogen gas will be means that the V will be some value. Just I have already calculated. Okay, V will be like 11.24 meter cube or 11 11.24 meter cube. 11.24 meter cube means that how much liter?
It is 11240.
Okay, at NDV. If you calculate the value at 350 bar, at 350 bar, the volume of the hydrogen gas, suppose it will coming that the 0.042 is a meter cube,
So
means that
42
the
liters.
42 liter. If you calculate the volume of the hydrogen at 700 bar, the volume of the hydrogen gas is coming that the 0.025 meter cube means at the 25 liter. If you uh, at liquid state, at at liquid state, liquid state, suppose if you calculate volume of the hydrogen, the value will come like if you calculate the value, will come will that the 0.01 0.01 meter cube. That means the
10 meter, 10
one
liter. 10 liter.
10. That is the 10 liter. For the
Sir,
solid case, huh,
yeah, sir, correct. Yes, sir. Finish it
I
then.
am coming. For the solid, the total volume requirement or total volume of the hydrogen, occupy volume of the hydrogen, the solid case. Suppose this is the solid case. Sorry, actually, I have put it some wrong. Sorry, I have taken some wrong data. It should be solid. For the solid case, it should be 0. This should
Okay.
be 0.01 meter cube. If we calculate it, you can get it. Okay, this will be 10 liter. This will be 10 liter, and this will be like 14 liter. This will be 14 liter. That
1 4.
means 1 4,
After, yeah.
1 4. This is okay. So you can see the main whatever the motto of the first class was, the hydrogen should be compressed at solid state, liquid state, such that the cylinder. So for the hydrogen gas at NTP conditions of 1 kg of hydrogen, for storing 1 kg of hydrogen at NTP conditions, you have to require this much liter of tank. So this is a very large amount of the tank. Is it possible to make this large liter content tank? 11,240 liter tank can you made?
Yeah, it can be made, but not convenient.
But not convenient, or not easy to handle also.
Yeah,
Okay,
not
okay.
practical also. Yeah.
Not practical, impractical. Okay. Is it possible just for 1 kg, just for only 1 kg of hydrogen, 42 liter of tank? Okay, suppose in your motorcycle, 5 kg of hydrogen at a time you should keep. Okay, for that 5 kg of hydrogen, you have to make 200 liter of hydrogen, 200 liter of oil tank. Is it possible? No. Okay, so this is also very high actually. This is also very high, and this is somewhat acceptable, 25 liter, but this is also high. Okay, but somehow acceptable. Okay, so 1 kg of hydrogen, for storing 1 kg of hydrogen. Okay, at higher pressure, if we increase the pressure, is increased, the volume of storing 1 kg of hydrogen is reducing, or container volume is reducing. Okay, so hydrogen should be storage in a compressed manner. Okay, for the storing of the liquid hydrogen, only the 14 liter of tank can store 1 kg of hydrogen, or 10 liter of tank fuel tank can store 1 kg of hydrogen. Okay, this is the our main comment. Okay, okay. This is all about for the today's lecture, and we'll
But
meet in the
another, I
next.
think another part of this last question is remain. Finally, comment. Okay,
Oh,
finally,
okay, 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 okay. Final comment. Finally, comment on hazard related issue when leakage occur from the liquid hydrogen storage tank. Okay. Suppose I have to make one extra slide. The question is asking that if hydrogen gas is, this is very interesting or also important actually for understanding. Suppose suppose if the hydrogen gas is storing in a liquid condition. Suppose this is liquid storage hydrogen tank. Okay, this is liquid hydrogen storage tank. Okay, the liquid hydrogen storage tank. Suppose liquid is storing at 77 77 Kelvin. 77 Kelvin. This is very minus degree centigrade. Okay. Suppose this hydrogen, liquid hydrogen, if leakage take place, suppose this is atmosphere, this is ATM conditions. Okay, atmospheric conditions. If this hydrogen gas leak from the storage tank, what will happen? This is your question. What will happen?
yes, one effect. What I can understand that there will be some Joule Thomson effect uh, near the leak point, because
Exactly.
from high pressure
Uh,
to low pressure, I mean, yes, high
expansion.
pressure to low pressure is
expansion.
coming.
Exactly.
Expansion
The
will happen.
uh,
So,
the
if
uh,
so
Joule
from,
Thomson Joule Thomson will occur. So it is throttling process will occur actually. Okay.
yes, sorting
So
process, and
so means that
some
the
ice will form, as ice will form outside the tank near the
uh,
leak.
high pressure to low pressure, and one thing, very high expansion. The expansion will be very high. Expansion. Expansion of the hydrogen gas. PAN expansion will be very high. Expansion means that the smaller, firstly the one cloud will form of liquid hydrogen cloud will form. Okay, and this is will be the liquid conditions, and atmospheric conditions when it will expose. Then this liquid will convert into the gas. The gas will the hydrogen gas at 300 atmospheric 300 Kelvin or 298 Kelvin. This will expand means of the very larger volume. And how much the larger volume? Okay, can you calculate the how much the larger volume? If we the V volume of the hydrogen for the liquid to suppose volume of the hydrogen liquid to gas volume of the hydrogen is the gaseous condition at atmospheric 1 atm. What was the volume 1 kg of hydrogen? Suppose 1 kg hydrogen has been leaked. So volume of the liquid hydrogen
It
what?
was, yes,
14 kg. 14, 14,
14,
14,
yeah,
14
14
liter.
liter.
14 liter. 14 liter means 14 liter. Okay, 14 liter. And the gaseous, the first one was like I think
NPP, NPP. It was
NPT
NPP,
11 point
something 11,000
11,000
11,030.
to 40 liter.
liter.
Okay, so 1 liter, suppose 1400, suppose 1 kg hydrogen gas has been leaked from this container. This 1 kg of hydrogen, when it will come to the atmospheric conditions, it will occupy the 14 liter space. This is 14 liter space occupy, and when it will convert it into gas, it will occupy 11,240 liter space. So means that the
11
11
meter cube. Yeah, 11 meter cube.
or 11 meter cube, it is 11 meter cube. Okay, so it is very larger
Yes.
volume. Okay, so hydrogen will be quickly spread quickly spread all over the matlab, I mean throughout
No,
the.
sir, it will not be very much, because like our one of our room, which is 10 by 10 by,
No.
so it will be
Okay,
about 11 meter cube, like.
okay, if the hydrogen tank will not be in your room, hydrogen tank will be in the open atmosphere, then
Yes,
if the leakage will occur, what the volume of the hydrogen gas will take? Okay, this is the thing. Okay, this is the some sort of practical type of thing you have to think. Okay, and one or two,
okay.
also the all one or two numerical is also important, but due to the less time I'm unable to solve, or you can see the
Sir, can you show that only I can take a screenshot of that?
bus I will give you the slide in PDF
Yeah,
form.
slide
Okay,
poster in this. Sure.
in the
Okay.
PDF form. Okay, and just I am discussing the thing, whatever the solve. Okay, the question number 2: calculate the work done to compress 1 kg hydrogen from 1 bar to 16 bar isentropically, assuming hydrogen as a linear gas. assuming hydrogen as a ideal gas, if the compression is done two-stage compression from 1 to 9, then the 9 to 16. In the first case, you have to calculate the isentropically hydrogen compressor work done. So isentropically formula is, what is the isentropically work done formula? Work done formula isentropically. Isentropically work done formula is the gamma divided by gamma minus 1 into
One
R into T multiply third bracket final
P2 by
pressure
P1.
final pressure divided by P1 to the power just it is just upward direction gamma minus 1 divided by gamma for your better understanding. This is 1. If you put the value, the what is the first questions, 1 kg of hydrogen, 1 bar to 16 bar. So 1 bar to 16 bar, your P1 will be 1 bar, and P2 will be your 16 bar. And taking the gamma as hydrogen is bimolecule, so diatomic, so gamma will be 1.4. So and R equals to 8.314. R equals to 8.314. So all the values are given here, gamma, R, P1, P2. You can calculate the work done isentropically. If you calculate the work done isentropically, you will get what value you will get? Sorry, this is what value you will get? You will get negative value or positive value.
Yes, isentropically calculate the work done to compare. It should be negative because
Should
we are
be
compressing.
yeah. It should
I mean, we are
exactly,
applying
exactly.
work to the
The
system.
work done. It is in the negative value. Okay, it should be on negative value or job. So suppose the answer is the this one. So
9122 in your
now
calculation. Okay, okay.
this
1047.
10476 kilojoule.
Yeah.
This 1047 kilojoule it should be in this form. I mean this amount of the work you have to give
Apply
for
to the
compress
system.
apply to the system for compress the hydrogen. Okay, next questions is the two stage compression.
In answer,
Hmm.
there are in answer if it is given like one option 10476, another option minus 10476. Which one we should
No, no, no,
give?
no. In always the options will be in the plus form. The question in the questions you will be asked that what will be the work input to the system. So this much amount of the work input to the
Okay,
systems.
okay,
Okay,
okay, okay.
work input to the systems means the minus, but amount of the
Hmm.
work is the scalar quantity. The next question is the compression from the two stage compression. The compression first compression from the 1 bar to previously it was directly 1 bar to 16 bar. Now the two stage compression it is 1 bar to 1 bar to 9 bar, then the 9 bar to 16 bar, two stage
Hmm.
compression. You will
Yes.
use the same formula P1 P2 and another formula. You have to another formula, the same formula, just you will write the P3 divided by P2. Okay, all keeping all the things same. You will get the less amount of the work because you are using the two stage compression. Okay,
Okay, okay.
okay. This is the questions. And another questions is very simple questions. Question number 3. Calculate the work done to the compress 1 kg hydrogen isothermally. Previous questions were isentropically compression. Now is the isothermal compression.
Hmm.
The final volume reduced to one fourth of the initial volume. Suppose final volume V2 is one fourth of the initial volume. So V1 equals to 4 V2. Okay. Temperature is 298, R equals to 8.314 kilojoule per kg Kelvin mole. Okay, as it is kg, it is not mole. Okay, this unit is also correct. Okay, So isothermal work done equals to isothermal isothermal work done formula is RT ln
ln,
V2
yes,
V2
P2
divided
by,
by V1. So
or
you know the
you,
R value, you know the T value, V2 value, you know the V1 value. I mean, in the case of the V2, you just keep the V2, okay, or V1 in place of the V1 for V2. V2 will cancel, and you will get the minus 34,364 kilojoule. Okay, that means that means this is the minus value. So minus, you are getting the minus value, minus work done. That means you are giving this much amount of the work to the system, okay, for compressing the hydrogen, okay, for 4 time compression. Okay, the question is, here the question is also find the amount of the heat evolved and change in internal energy. You know that as it is isothermal compression, as it is a isothermal th here, isothermal compression,
there
the
will be no change in internal energy.
internal energy du equals to 0. Why no change in internal energy?
Because
Because
the
internal
so
energy
due to the temperature change, the energy inside changes.
huh,
But here the
because
temperature is same.
because internal energy is a function of temperature. Internal energy is a function of temperature. What is internal energy? Internal energy is the, suppose in a confined space, any gas molecule, if we increase the temperature, it will get some, it will gain some kinetic energy. It will move
Move fast.
uh, move fast, or random
Random.
motions, highly random motions will be there. This is internal energy. Okay, so temperature will be high, internal energy will be high. So at a constant temperature, change of internal energy at the same temperature, change of internal energy will be 0. So answer is our d, change of internal energy will be 0. And another question is the change of evolved heat. What is the total heat generation? So from the first law of thermodynamics, we can say that the dq equals to du plus dw. Here our dw, as it is the isothermal process, du equals to 0 and dq equals to, so we can write that the dq equals to dw. So total heat generation equals to total work done. Okay, so total heat generations will be 3434.64 kilojoule. Okay, for if we compress the hydrogen 4 times from the initial value. Clear?
Sir, here the sign convention will be very confusing because the DQ also minus and work done also
Okay,
minus.
okay, I just yeah, I am coming to the part. Okay, I am writing another color, actually black. Okay, the sign convention, suppose this is systems, you are compressing hydrogen. You are compressing hydrogen means this is the hydrogen systems. You are compressing hydrogen means that you are giving some, you are, you are, you have to give some work to the system.
What?
You have to give some work to the systems. I already told you that the, if the work is given to the systems, that means this work sign convention will be minus. Okay, if you get some work from the system, if you get some work from the system, the work will be positive. Okay, clear?
Yes, sir. Yes, sir.
Yes. Okay, so work is negative in our case, and we know that if we give some heat, if we give some heat to the system, if we give some heat to the system q, it will be negative.
Negative.
So sorry, it will be positive. It will be positive. If we apply some heat to the system, it will be positive. If some heat is released to the from the system, it will be negative. Just opposite of the work, minus V. Clear? If we compress the hydrogen, the work is given to the system, so work will be in minus.
Negative.
So work will be minus, and if we compress the hydrogen, some sort of heat energy will be generated, temperature rise will be there. So heat energy will be produced. So how much heat energy will be produced? 3434 3434.64 kilojoule. 3434.64 kilojoule heat energy will be produced. So our our so dq equals to dw from the thermodynamics first law. So our dw equals to minus. So our dq will be also minus 3434
Yes, yes.
3434. So here dq equals to minus. Minus means heat is generating from the system.
Getting from the
You are getting heat from the system. From the system you are getting heat.
It is released.
So our sign convention matches with our thermodynamics first law. Clear?
Thank you, sir. Thank you.
Okay.
We have overrun today, sir.
Yeah.
Time.
Okay. No issues.
Thank you, sir.
Okay. We'll meet in the next session. Okay. Now you can leave.
Thank you, sir.
Okay. Welcome.